So now I'll work through a particular case of the extended Euclidean algorithm, and we'll do it in such a way that we'll see the method clearly generalizes. So first of all, you recall we had the Euclidean algorithm itself, in which we computed the greatest common divisor of 3, 5, 3, 6 and 1, 2, 7, 5, and we found it was 17, and these were the lines of the argument. We ended up here with 17 as the greatest common divisor. So now we're going to work backwards through this argument, through the Euclidean algorithm, and this will be in effect the extended Euclidean algorithm, which will allow us to express the greatest common divisor, 17, in terms of a sum of multiples of the individual numbers 3, 5, 3, 6 and 1, 2, 7, 5. So it'll be 22 times 3, 5, 3, 6 plus minus 61 times 1, 2, 7, 5. And as I said, we're going to work backwards through the Euclidean algorithm here on the left in order to obtain that. And we'll do it in a systematic way. So first of all, from this line here, we can express 17 as a sum of 119 and minus 2 times 51. So I'll write that here. 17, which is the greatest common divisor of those two numbers, is 119 minus twice 51. Now, the 51 from here we see is itself a sum of multiples of 289 and minus 2 times 119. So the 51 we can express here as 289 minus 2 times 119. That's using this line here. Now if we just then follow on, we have 119, 119 here, and then 289. So we end up with, doing the calculation, we have minus 2 times 289, and we have 5 times 119. Now, again, we're going to find that we can express the smaller of these two numbers, 119 and 289, by using this line here. 119 is a sum of 986 and minus 3 times 289. So we do that and we get this. So now we've expressed the greatest common divisor, 17, in terms of 986 and 289. Now 289, the smaller of those two numbers again, we can use this line here and write that 289 as 1275 minus 986. So this here, we substitute 1275 minus 1 times 986. And then we have the 17, and we have the 5 times 986. So doing the calculation, you end up with minus 17 times 1275 plus 22 times 986. And again, 986 now, the smaller of these two numbers, we use this line here and express it in terms of the 986, that is 3536 minus twice 1275. So we plug that, replace that, and we put that into here. So we end up with what we want by working backwards through the Euclidean algorithm, that the greatest common divisor, 17, is minus 22 times 356, that's this, minus 61 times 1275. And that's our result. So we've now shown that. And what happens if, for example, we're looking at the greatest common divisor of a situation where one of these, or that one, let's say, is negative. So we have this situation here. Well, we know the greatest common divisor itself for this and this is the same. Doesn't matter if we change signs here, from here. And we also have this expression. So the 17, which is the greatest common divisor there, is, we're going to write this as instead of 22 times 356, we're going to write it as minus 22 times minus 3536. And then 1275 is the same as up here. So there we are. The multiple, if we change the sign to minus 3536, then we just change the multiple to minus, in this case, 22. So it's clear that in general we can find the multiples s and t even in case the numbers here are no longer both positive.